In the video, I discussed this, that we only have two integration techniques. I've been framing it in this way today. One way is change the way it looks using algebra. We also saw we use trig identities. To be honest, we do this more in Math 5B. And the second way is the substitution rule, which is what this section is about. So this is just reinforcing the idea that when you don't have limits of integration, you talk about an antiderivative, which is the same as the indefinite integral. Okay. And when we're doing this U substitution, we're really undoing the chain rule. So the basic idea is you are going to take a complicated looking integral, and after you make the correct substitution, your integral is going to look far simpler. But it's going to look simpler, but it's going to be in terms of a different variable, u. And then you're going to integrate everything in terms of u, and then you're going to switch back to x. Okay. So when you do u substitution, you're really looking to see what can I let u be so that my integral looks far easier. Well, at the same time, you're looking to see that the derivative of your substitution is sitting there. So I did example 1 for you in the video. In example 1, if we look at this, this is a complicated looking integral. I noticed that if I let u be the thing inside the parentheses, the derivative is sitting right off to the side. That means if I let u be this, I can take the derivative like so. And what I can do is I can solve for du. And you see when I solve for du by moving the dx up here, I'm treating these as differentials. Then you'll see that I have this 2x dx, and that's exactly sitting right here. So this complicated expression here gets replaced with the u cubed, the 2x dx gets replaced with the du, and now I'm left with a very simple looking integral. But that's in terms of u. I take the antiderivative, and then I substitute back. So replace the u back. Okay. So this is how integration with substitution works. Let's take a look at example 2. In example 2, I need to figure out what my u should be. Does anybody have any guess as to what my u should be? Type your answer in the chat box if you have any feeling. Terry, I think that's a good guess, or not a good guess. That's good. Does anyone else have a suggestion for you besides Terry, who messages me privately every time? No. Everyone else? Oh, yes. They will both give the correct answer. So remember, you always want to let u be so that your integral becomes simpler. Something complicated to the third power, that's a clue. Maybe I should let u be this guy. So I'm going to let u be equal to 3x squared plus 17. Then what is my du going to become? My du dx is going to be equal to 6x plus 0, right? Take the derivative of both sides. And this means that my du is equal to 6x dx. And if you look, that is exactly sitting right here, 6x dx. So now I'm going to make my substitution. It's going to be u cubed. And then I replace the 6x dx with a du. Is there any questions up to this point? Because if you can get this far, it's easy to do the rest of the problem. But if you don't see why the substitution is what it is, you don't see why the 6x dx gets replaced with the du, then It's a lot harder, I guess. No questions? So then I'm going to integrate. So this gives me u to the fourth over 4 plus c. Now we still need to put the u back. The original question was in terms of x. So this needs to be 3x squared plus 7 to the third power divided by 4 plus c. And that's going to be your answer. Is there any questions about this? We can check our answer too by taking the derivative. Do you remember at the beginning of this class, I talked about verifying that, oh wait, that's a 4. Thank you. For sure, it's a 4. And we could verify that we did it right. If we take the derivative of this, we should get the inside here. So let's just verify by taking the derivative in green. If I take the derivative, that's going to be 4 something to the third power, 4 over 4 something to the third power. I keep the inside, which is 3x squared plus 7, multiplied by the derivative of the inside. The derivative of the inside is 6x. So the 4 and the 4 cancel each other out. I can see, oh, when I take the derivative, I get the same thing. So this was it. This was check. Make sense? Let's take a look at example 3. If you take a look at example 3, what do you want u to be? Oh, 17 instead of 7. Whoops. Oh, you're right, Ken. Thank you. Can I just squeeze it in there? I wrote 7 instead of 17. There's a 1 there. And there's a 1 here. Sorry about that. All right, folks, can you guys see what my u should be for example 3? What do people other than Terry think? People that speak out loud to everybody. Anyone see what u should be? Okay, Terry, why do you think u should be z squared minus 5? Do you have a good reason? Because you're right. I'm just wondering if you have a good reason. You could unmute yourself if you wanted to explain to us. So you don't really know how to take the antiderivative of the square root of anything complicated. All you know how to do is take the square root of x or the square root of u. So when you see this complicated expression inside the square root function, that's really a clue that you want to let u be that. At the same time, you realize you should see the derivative of the inside sitting to the side up to a constant. So when I calculate the derivative of u, I get 2z. So that's du dz is equal to 2z. So I don't exactly see a 2z up here, but I don't really need the 2. The important thing is I need the z. So a lot of times when I teach this substitution method of integration, I do it by working with differentials. We had talked about differentials before. Differentials is where we think of du and dz as separate quantities. So this should be du is equal to 2z dz like this. And then we can solve for dz. This means dz is equal to 1 over 2z du. So now I'm going to make my substitution. When I make my substitution, I'm going to get the integral. I'm going to temporarily write a z here I'm going to get u to the 1/2 power. And I'm going to replace the dz with 1 over 2z du. Now, it's really important for me to mention that all the z's need to cancel out so that everything is in terms of u. Okay. In this case, that does happen. The z here and the z here cancel each other out. So our integral becomes 1/2 integral of u to the 1/2 du, like that. And now we can just integrate. You get 1/2 u to the 3/2 times 2/3 plus c. That's equal to 1/3 u to the 3/2 plus c. Is this my final answer? What do you think? Are we done? Why not, Luciano? We got to substitute back to x or z. Substitute back to z because the original question was in terms of z. So this is 1/3 z squared minus 5 to the 3/2 plus c. This is our final answer. Good. Any questions? So let me just make a couple comments here. For these earlier guys, I substituted the du in directly because I saw the exact derivative sitting off to the side. Example 1 was like that. Example 2 was like that. I see the exact derivative, this 2x dx, and it's exactly sitting right there. So that allowed me to put in the du part right there. But in example 3, I just have a z here. I don't have a 2z. So what I did was I solved for dz. And if you do it in this way, you're going to be substituting in stuff that has z's in it. So I really wanted to emphasize that all the z's need to cancel out.